All righty. Well, hello, friends. How we doing today? Okay, so we got an idea now, a little bit about what a limit is. A limit is when the graph is approached to the same value on both the left and the right side, both the positive and the negative side. When the graph goes to the same point, the same value, then the limit exists. So we're going to look at that a little bit more, but this time, instead of a graphical idea, we're going to look at it more from an analytical idea. In other words, we're just going to do some pretty much some plug and chug type stuff. So how do we evaluate the limit of a function when we know what the expression is? So the limit as x approaches -1 of x squared plus 1. And we're going to do a few more just for the fun of it. So all of our arithmetic rules for limits still hold true. There's one kind of a weird rule we'll talk about in a second. So we have cosine of x times the square root of x plus 4. And we're approaching 0 on this one. And then the last one here is the limit as x approaches, let's go 5. Of x squared plus 25 and 3x minus 5. Okay, so if we think back what we did with limits last time, let's think about what's actually happening here. So this whole little part right here is really, it's as if we were saying that this is some function. So it's like saying, hey, given the function f of x equals x squared minus 3x plus 1. Those are horrible too. There we are. What we're really being asked here is, if this is what x is, in other words, instead of x, we're going to plug in -1. We're asking ourselves, really, how do you evaluate that function when x is -1? So that's really what's going on here. We're going back to pre-algebra. Given a value of x, plug it in. So let's try that. We're given a value of x, we plug it in. Now, when we get to the AP test, we actually will leave our answers like this. The College Board never makes us simplify expressions, which is awfully nice of them. But you're in my class, and I'm going to make you simplify. So we plug it in, and then it's just a matter of getting the actual answer. So 1 plus 3 plus 1. So the limit equals 5. Once we plug a number in, notice how I'm going to the right. Notation-wise, we want to just keep going to the right. If we ever go down, that brings in some notation issues that we'll talk about in a little bit. For the time being, go to the right. So all we're doing is just plugging our numbers and getting some values. So why don't you guys do me a favor, go ahead and pause the video real quick and plug in the values. All right, here we go. So we're plugging in 0 for cosine. So cosine is 0 times the square root of 0 plus 4. One thing you always have to simplify in calculus, you're never allowed to leave any trig function that can be simplified. You're never allowed to leave it alone. You always got to simplify trig functions. So they do dock you for that, but they would allow you to leave your answer as 1 times the square root of 0 plus 4. So 1 times 2, that would be dos burritos. All right. 2. Let's keep going here, friends. Let's keep going here. We plug our 5 in here. All right, so 5 squared plus 25. Throw that in there. All righty. And we get 3 times 5 minus 5. And we end up with 50 over 10, which is 5. So When I ask you to evaluate limits analytically, it just means plug the number in, evaluate it, figure out what it is that you're actually dealing with. So all our rules for logs, they're still going to hold true. Now, there is one log that's a little bit weird. Not log, one limit that's a little bit weird, and that's this one. So let's see here. It involves compositions. Let's let C be any real number. So as x approaches some real number, as x approaches some real number, and I ask you guys to evaluate some composition of functions. Compositions are a little bit different because you saw before, like when we did the limit of zero of cosine of x and the square root of x plus 4. What we really were asking here is we were multiplying two functions together. It is like we were multiplying f of x together, some f of x function, times some g of x function. And it doesn't really matter. When that happens, you just plug 0 in for both functions and you evaluate. Compositions are different. In compositions, you don't plug your c value into each function. You only plug it into the inside function. So this has a very special limit to it. We're only evaluating the limit for the inside function. And it kind of makes sense, because once you plug it in for this one, you're going to be looking for the y value of the other function. Now, there's a little bit more I would do with notation if we were actually dealing with the theorem of it, but it's not going to really come into play for what we're dealing with, so I'm not going to worry about it. So, for instance, here's how this works. Say I give you a function, f of x. Let's let f of x be equal to 1 over x plus 2. And let's let g of x be equal to the square root of x. So if I ask you to tell me what this limit is, let's go with as x approaches 4 of f of g of x, what value would you come up with? Why don't you pause the video and see if you can actually take a shot at that real quick. All right, so if we're doing it here then, so we're going to take this outside function and we're going to use it to evaluate the inside function with the limit. So we're going to take the limit only of the inside function. So our g of x function is the root x. And once I get this value, then I will go ahead and I'll plug it in for my next function. So if I plug 4 in there, I get f of root 4. So I'm looking for f of 2, which is 1 over 2 plus 2. So 1/4. So analyzing limits, not that bad. You just plug and chug. And if that's all it was, then hey, this would be a real short day. We call it and move on. But that's not quite all we're looking at. You see, sometimes limits don't work. We've already seen sometimes you have functions that have essentially values that just don't happen. So we have a little theorem. It's a good theorem. It says if two functions are equal at every value of x except for 1, or I should say let two functions, that'd be better. Let two functions be equal at every value of x, call that f of x, just for the fun of it. So we know what two functions we're talking about. Equal at be equal at every value of x, except for 1. Let c be a real number again. So any real number, it doesn't matter. And we're going to let f of x be equal to g of x for every value except x equals c. Then, if the limit of g of x at x approaches c exists, then the limit at of f of x also exists. And I'll write the and here in a second. I forgot one little part. For every value except, and let f of x be for every x value as well as f of c. For every value on the open interval. That's what I want. All right. So let's add a little bit more here to our theorem. And then, like I said, this is a big theorem. So I want to write it all out there as if you would see it in a calc class, and then we'll talk about it. I'll see if I can't try to give you an idea of what this looks like. Okay, so we have two functions, f of x and g of x, and we're going to let them be equal to every single value except for 1. So how would we know if two functions are equal at every single value except for 1? So let's take a function here. Let's take the function f of x. And let's say that this function right here is x squared minus 3 of x plus 2 over x squared minus 4. I'm going to suggest that I believe that this function right here is the exact same for every value on this function, except for, I think they're the exact same, except for when x equals, the only time they're not the same is when x equals 2. Other than that, these two functions would be the same. How do we know that? Let's just take this for a second. If we were to factor the top, just like we did back in Algebra 2 and pre-cal, we end up getting an excluded value. And we said when we're dealing with functions, that excluded value is where the graph would have a hole at. So that means this graph right here would be at, it's the same thing as x minus 1 over x plus 2. And this is when we did our excluded values for our hole, except for x doesn't equal 2. In other words, over here, for g of x, x could be equal to 2. But for f of x, they're the same function, it's just x can't be equal to 2. That's what we mean by the same function. So it's the exact same, except for one x value. In this case, x equals 2. In other words, what that means is, if I were to take a limit, and let me show you what I mean here is, if I were to take the limit of f of x at x approaches 2. If I were to take it and plug it in here, I would get something that wouldn't work. So when I plug my 2 in there, I would end up getting 4 minus 6 plus 2 all over 4 minus 4, which would be 0 over 0. That doesn't work. It was what we call indeterminate form. So this form of 0 over 0 that's called indeterminate form. In other words, we are in a form where we can't determine what our value is. So if we could rewrite this, we could actually figure out a form that we could actually solve. And that's what this says. Hey, if you can't figure it out in f of x, but you know that g of x works the exact same except for one value, in this case, that value x equals 2, we could actually figure out what this is. So once we've shown that a limit is indeterminate, we can go about rewriting it in terms of that g of x function. So I would start back, I'd go back to the original function, x squared minus 3x plus 2, that original expression. And what I'm going to do now is I'm going to manipulate it until I get it into that value that actually works. So in other words, I'm going to factor the top and bottom. Now this is where calculus, the form kind of becomes important. Even though I'm using an equal sign, if I'm not evaluating a number, if I'm rewriting a limit, I have to keep writing limit in front of it. So x minus 2, x minus 1, all over x minus 2, and x minus 1. And from here, our x minus 2's would cancel out. And so we'd end up with a form that we actually can play with a little bit. So x approaches 2, I'd have x minus 1 all over, that should have been a 2 right there, plus 2. I apparently struggled with factoring there. All right. And I end up with a form that I actually can evaluate. So now from here, I can go ahead and plug in my 2. So 2 minus 1 over 2 plus 2. Because this limit right here can be evaluated. So you all of a sudden you start to see where that g of x is that they're talking about. You see that right here. I can evaluate this one. And this limit right here is the same as this limit right here, except for when oh, they won't let me draw another rectangle. That's interesting. Except for when x equals 2. They're the same. And since they are the same, I can rewrite it. And if I can evaluate it in this one, that means that this limit right here, where that hole would have been, would have had to have been the same value. So although I couldn't determine it in this form, I was able to change its form. And now I can actually say what the limit is. So the limit then as x approaches 2 of x squared minus 3x plus 2 all over x squared minus 4. So even though that was 0 over 0 to begin with, because I was able to evaluate it in its other form, I'm actually now able to say what this is. This right here, this is one of the ways we can rewrite. It's called we can evaluate by factoring. And some people call it dividing out. So we're factoring it we're evaluating it by factoring out or dividing out. So that's what this one is called. So let me give you another one that you'd have to actually go ahead and see if you can do this idea of evaluating it by factoring out. So remember, first prove that it's 0 over 0, and then from there, go ahead and divide and factor to make it something you can actually deal with. So here's your problem. The limit as x approaches, well, we're going to use -3 on this one. Let's try that. And I'm going to give you 2x squared minus 5x, or plus 5x, minus 3, all over 3x squared plus 14x plus 15. All righty, friends, why don't you go ahead and pause the video and see if you guys can actually figure this one out. It's always fun to take my magic eraser here. And again, this is called factoring out or dividing out. All right, so if I were to go through, the first thing we always got to do is got to first make sure that it actually works. So if I plug in my -3, I get 18 minus 15 minus 3 all over. If I plug my -3 down there, I get 27 minus 42 plus 15. Because if this ends up not being 0 over 0, then there's no sense going. I might actually get the answer. So we always check. Okay, so this is indeterminate. So once I know that's indeterminate, now I move on to the next part. Now I can go ahead and start factoring out. So I know that that didn't work. So you guys can write a whole lot faster than I can on the screen. So I'm sorry if it's taking a little bit of time. Whoa. (14x plus 15). All right, so we're going to go ahead and factor it here. So since I'm going to keep rewriting it, I have to bring the limit with me. I don't get to just drop that. That's one of those form issues. And I believe I'm going to end up with, let's see here, 2x. Oh, let's go -1 and x plus 3. That looks like that factor's pretty good. Let's go with 3x. Let's see, what am I feeling here? Oh, 5 maybe? And x plus 3. All right, so from there, we can see that the x plus 3's, they factored out. So I'm going to go ahead and evaluate this now. But once I get those x plus 3's out of there, so I have 2x minus 1 over 3x plus 5. And now we can plug our -3 in there. So now that I'm plugging the number in, I don't have to write limit anymore. So I have -6 minus 1 all over -9 plus 5. So -7 over -4, which is 7/4. So that means our original limit then as x approaches -3 my handwriting is getting a little bit sloppy. So that means this whole thing then is equal to 7/4. force. Okay, so we're able to evaluate by factoring out, by dividing out. Well, that's not the only way we can factor out. Or that's not the only way that we can evaluate something analytically. Let's take this one. The limit as x approaches 0, root x plus 9 minus 3 all over x. So if I plug in my root 0 in here, or my 0 in here, I get root 9 minus 3 over 0. So again, I end up with something that is indeterminate form. In other words, the form doesn't work. So this is going to go back to something we did back with imaginary numbers. And we used to try to say you can't have an imaginary number in the denominator, so we'd multiply by its conjugate. Well, we can do the same thing with, and we did the same thing with radicals too. We just multiplied the conjugate of the radical in the denominator to get it out of the denominator. But we can do that same thing with our numerator. So in other words, here's what we're saying. Right now in this form, this problem doesn't work. It was indeterminate. But if I can multiply the top and bottom by something, which is we called rationalizing, then I can change it to something that would work. So what if I multiply it by using our difference of squares idea? So same thing, plus same thing. Now I have a minus b, a plus b, and there's my difference of squares. And if I multiply by that, so I rationalize that, I end up creating a limit that I actually can evaluate. So in other words, by doing that, when I multiply the top, so I'm going to square the x plus 9 minus 9. And on the bottom here, I am left with an x times the square root of x plus 9 plus 3. So the 9s are going to go away. And then I'm left with an x on top. Oh, better not forget my limit. I'm left with an x on top, and I have my x on the bottom. So x plus 9 plus 3. So from here, then our x's would cancel out. And lo and behold, I'm going to make sure at this point, I clearly know that there will not be a 0 anymore in my numerator. I'm able to rewrite it in a form that I actually can evaluate. So my x's go away. I'm left with x plus 9 plus 3. So when I plug my 0 in there, I get 1 over root 9 plus 3, which is going to be 1/6. Well, that wasn't very good. How did we pull that one off? Also not what I wanted. How do I get back to that? There we are. So you can't, just learn something. You cannot leave the whiteboard. Didn't know that. All right, here we go. So we got 1/6. So that means this limit right here, I couldn't do it before, but now I can. This limit then is equal to the of x plus 9 minus 3. Turns out this whole limit equals 1/6. And this is called rationalizing. We evaluate by rationalizing. So let's have you guys try one. What if I give you the limit? Let's not do that. Let's go back to black. The limit of x approaches 6 the square root of 3x minus 2 minus 4 all over x minus 6. All right, why don't you guys try that one? All right, go ahead and pause the tape, and I'll see you in a second. Okay, I think we're ready here. So first thing we want to do when we're rationalizing is we got to make sure that we have picked, that we've shown that it is indeterminate. If it's not indeterminate, we don't go any further. So if I plug my 6 in there, I get the square root of 16, which that's 4 minus 4. There's my 0 in the numerator. 6 minus 6. Okay, so that's my 0 over 0. So we're going to go ahead and rationalize this one here. As x approaches 6, we got one more we're going to be doing after this one for today. And then we'll call it a day. We'll deal with the rest of this later. So we're going to multiply by the conjugate. So that'd be plus 4. So I have multiplied the top here. Got to multiply the bottom as well. So here comes our limit. So the limit as x approaches 6. So if I square the first part, the radical goes away. So 3x minus 2. And then I have negative 4 times positive 4. Well, that'd be a negative 16. And then I have parentheses x minus 6. And I have my other parentheses. One of the biggest things people mess up on is just forgetting parentheses. So don't be bashful with them. Plus 4. So right now, this doesn't really look like it's doing what we want it to do. So let's see what happens here. I combine my like terms. I get 3x minus 18 on top. I have x minus 6 on the bottom. And then I have my radical 3x minus 2 plus 4. Well, on the top, I'm noticing that I can factor 3 out of here, 3 out of that. So let's go and factor 3 out of that. So 3x approaches 6. Oh, this is what I wanted. There's my x minus 6. And my x minus 6 on the bottom now. So now when my x minus 6's go away, I'm going to be left with a 3 in the numerator. And on the bottom, the root 3x minus 2 plus 4. Now I can evaluate. So 3 all over the square root of 16 plus 4, which is 3/8. All right, you guys are good sports here. This is the longest lesson in this unit, so you guys are being good sports here. I appreciate it. My friends, I wish I could be doing with you guys in the classroom, but that's okay. And good news is if you ever need to, if you miss something, you need to come back to it. Well, now we have it. So 3/8. It's evaluating by rationalizing. There's one other type one that I told you we're going to be dealing with today, and that's this one. Sometimes life doesn't work out so hot because we're dealing with fractions. So we have complex fractions. There you go. All right, so if I plug my 0 in here, I'm going to be getting 1/2 minus 1/2 all over 0. And that would be then 0 over 0. So this one, you see a complex fraction right now. I'm sure you guys can already figure out what we're going to do, but this one we're going to be able to evaluate by getting a common denominator. So we're going to evaluate it by using a common denominator. So didn't work for us. No harm, no foul. We're just going to have to change how this thing looks. So I have x approaches 0. So right now I have 1 over x plus 2 minus 1/2 all over x. Now let's remember what this x is here. This x is the same thing as x over 1. So I need to get a common denominator. So everything that's in the denominator, I'm going to multiply by. So I'm going to multiply. I see a 2 here, and I see an x plus 2 here. I'm going to multiply this one by 2 times x plus 2, and multiply this by 2 times x plus 2. Everybody's going to get multiplied by the same denominator. You can kind of see why they call this advanced algebra. We really, even though we're saying we're doing limits, we're really just doing algebra 2. Or for you guys, that would have been integrated 3. So we plug it in there. Now, if we clean this up a little bit, my x plus 2s here, well, they're going to cancel. And I'm left with just a 2. Minus, over here, my 2's cancel. My 2's cancel, and I'm left with a minus x plus 2 there. And down here, I have an x times 2, so that's a 2x. And x plus 2. And I'm not going to bother factoring that in there. There's no reason to do that. So when I keep going here to clean this up a little bit, I see a limit. I end up with 2 minus x minus 2. So I have a negative x on top. And on the bottom, I have 2x times x plus 2. So our x's are going to drop. And I have x approaches 0. I'm left with a negative 1 on top. And on the bottom, I have a 2 times x plus 2. And that's because our x's went away. Well, all my x's are in Texas anyway, so must make my home in Tennessee, but whatever. So I plug my 0 in there, friends, and I end up with negative 1 times 2 times 2, and that would be a negative 1/4. So again, I couldn't evaluate the first, but if I change the form of it, I can solve it. I can evaluate the limit. They agree at every point except for when x equals 0. So by evaluating something I can deal with, I can go back and say the first one would also have been that. All right, here's your last problem of the day to try. Let's go with the limit of, well, let's try x approaches 5. 1 over x plus 3 minus 1/8 all over x minus 5. All right, go for it. Go ahead and pause the video if you haven't done that yet. So hopefully you went back and did that. All right, let's do this, friends. Here we go. Last time we plug our 5 in there, and I get a 1/8 minus a 1/8. And I have a 5 minus 5. And friends, I can't be the one to tell you that, but that would indeed be a 0 over 0. That is no bueno. So this is where we're going to go through and rewrite it with our common denominators. So 1 over x plus 3 minus 1/8. And we're going to multiply everything. Oh, I forgot the x minus 5 down here. Now don't forget this x minus 5. I'm going to put that together as just over 1. So we're going to multiply everything by the common denominator. So we're going to multiply by 8 and x plus 3. There it is. And we're going to multiply this one right here by 8 and x plus 3. And last and certainly not least, we'll multiply this by 8 and x plus 3. So we'll cancel out those things that we just don't like. So the 8's go away, the x plus 3's go away. Well, it turns out this limit here then is going to be x approaches 5. Now I have an 8 in the top here, minus, looks like I have a minus x plus 3. And then I also have down here, what do we have? We have an 8 times x minus 5 times an x plus 3. So we clean this up a little bit here. And sometimes these aren't always completely obvious, but I've got a feeling you guys are probably putting this together. Here we got a negative x plus 5. Well, that's not so friendly. And I have an 8 and an x minus 5 and an x plus 3. And I don't know about you, but I am not feeling that negative x up there, so I'm going to factor out -1 from it. If I do that, I get a -1 times x minus 5 all over, there's my 8, there's my x minus 5, so those will end up canceling, and my x plus 3. So when we cancel this, we have -1 all over 8 times x plus 3. So plug our 5 in there, we get -1 times 8 And 5 plus 3, that was an ugly 3 there. That would be 8 there. So it turns out this whole thing right here, that's going to be equal to a negative 1 over 64. And again, this is called evaluating by using common denominators. So we write that one more time. And like I said, you guys are pros. This was the longest of all our lessons here in this first unit. So you guys did fabulous. So we first plug and chug to get our numerical value, but if our numerical value ends up being 0 over 0 or indeterminate form, no harm, no foul. We can either solve by factoring, solve by rationalizing the numerator, or we can solve by getting the common denominator. So friends, good luck today, and I will be talking to you guys tomorrow morning. All right, take care.